The figure shows a possible orbit of an object in the Sun-Earth system. It is called the horseshoe orbit because the shape of the orbit looks like a horseshoe. If the object is inside the Earth's orbit because its speed around the Sun is faster there than the Earth's around the Sun, it approaches the Earth from the right side more and more. At a certain distance from the Earth it will move strangely upwards, namely across the Earth's orbit. Outside of Earth's orbit, it orbits the Sun more slowly than Earth, and then moves away from Earth. This upward movement is believed to have been caused by the Earth's gravitational pull. That's a very vague interpretation, not entirely true. It is correct that the object is propelled upwards in the direction of rotation by the rotating gravitational field of the Earth, just as the Moon is propelled by the Earth. In the last video Recalculate Lagrange Points, Real Physics, number 20, we explained that the angular velocity around the Sun of a third body at the Lagrange point L2 is the same as that of the Earth. If a body is still some distance from this point, its angular velocity around the Sun will decrease, while that of the Earth around the same remains the same. Then its angular velocity around the Sun would be less than that of the Earth around the Sun, and it is slowly moving away from the Earth. Then he is outside of the control of Earth's gravity. Therefore, L2 can be considered as the highest point of a possible regular lunar orbit around the Earth. For a body to get to L2 naturally, its distance to Earth at point 1 as a starting point would need to be approximately 1.24 10 to the power of 9 meter. This distance is also the radius of the largest possible base circle of a regular Earth-Moon. Suppose a body is initially at point A, which is more distant from the Earth than point 1, then on an incline it will slowly move to the right and reach approximately point B. Because the Moon's speed around the Sun is slower than the Earth's around the Sun above the x-axis, it falls further and further behind the Earth. When at the end it is almost one lap behind the Earth, it approaches the Earth from the other side and approximately reaches the point C. Due to the rotating gravitational field of the Earth, the body is pushed down from point C to point D. Because the Moon's speed is faster than Earth's at this position, the Moon has a lead over it and is moving away from Earth to the left. After almost a lap lead, it reaches point E. At this position, the Moon is pushed up by the Earth's gravitational field and returns to point A. The process then repeats itself over and over again. This creates a lunar orbit that resembles a horseshoe. Of course we know that if a body is outside the Earth's orbit around the Sun, it runs slower than the Earth, faster inside. But the question is, why and how is its speed changed so that it runs sometimes slower and sometimes faster? The answer is quite clear, because the object's orbital velocity around the Sun was driven by the Sun's rotating gravitational field. Changing the object's distance also changes its speed. As already mentioned, the speed of a body driven by the gravitational field is always based on its orbital velocity, which is exactly the speed that is required to continuously orbit around a driving body. So the horseshoe orbit was created by the rotating gravitational field of the Earth and the Sun. This is clear evidence that the orbital motion of a body revolving around a central body is driven by the rotating gravitational field of the central body. Only in this way is it then possible to be able to walk one body around another forever. Thank you very much for your attention. See you next time.